In this video, what we are going to do is follow up on the last video where we're looking at converting between the open chain acyclic forms of monosaccharides and the cyclic forms. And in this video, to follow that up, what we're going to do is a couple of example problems to allow you to test your knowledge of that concept. So what I would encourage you to do is I am going to go ahead and bring up the problems here on our whiteboard. And once I have those up, I encourage you to go ahead and hit pause. Try to work through these based on your knowledge from the last unit and see if you're able to get the solutions to these correct. After you've got what you think is the solution, go ahead and hit play and continue onward to see if you got to the right structure, because when it comes time for the Canvas quiz, for example, you are going to need to be pretty sharp on doing these types of things, hint, hint. So looking at the examples here, we are going to be drawing alpha D-Galacto Pyranose as a Fischer projection. And also, as a follow-up to that, we're going to draw the open chain form of beta D-Glucosamine. And I've drawn each of these starting structures here for you. This is similar to the amount of information you would be provided if you're given this type of question on a quiz. So let's start with the example at the left. So drawing the alpha D-Galactopyranose as a Fischer projection. So first and foremost, that term pyranose tells us that we are definitely making a 6-atom ring through this reaction. And the way we make the 6-atom ring, similar to what we saw in the last video, is we use the penultimate hydroxy group, that is the next to the last hydroxy group of the chain, as our nucleophile. It comes up and attacks the electrophilic carbonyl carbon atom here of the aldehyde to form a hemiacetal in this non-enzymatic spontaneous reaction. And that spontaneous reaction generally favors the product side, the side that is cyclized. So that's why I've shown the arrow is not completely even. And since this is making a pyranose and our electron pushing arrows are going to show a 6-membered ring, I draw in my generic 6-membered ring Fischer structure template like so. The Fischer structure is a way of showing the structure and stereochemistry of the sugar ring by representing our 6 atoms of the ring like so, and then having these vertical bonds coming off to show the H and OH group at each position around the ring. So filling this in now, I always go in and number my carbon atoms, starting with the aldehyde group, going 1, 2, 3, 4, 5, and 6. Position 6 is the oxygen that forms the link to our carbon number 1. So that's that link right here. And so I'm going to color in or sketch in my numbers here corresponding 1, 2, 3, 4, 5, and I'm calling that oxygen atom number 6. And now we need to fill in the groups that are present here around the ring by keeping a few things in mind. First off, at that anomeric carbon atom, that's the first carbon out of the ring, the carbon right here, keep in mind that if we refer to this as an alpha cyclic sugar, alpha indicates that the hydroxy group at that hemiacetal anomeric carbon is oriented downward. Alpha means the hydroxy group is downward at that position. And so I'm going to go ahead and fill that in with hydroxy group oriented downward. So that is the hydroxy group that originates from this position right here. This oxygen picks up a proton and becomes this hydroxy group here in our structure. Alpha means that that is oriented downward. Then we come around the ring to positions 2, 3, and 4, and we ask ourselves what the orientation of the groups there is at positions 2, 3, and 4. The rule for that, as we learned in the last video, is that if the atoms are on the right in this Haworth projection, the open chain projection, that means those groups need to be oriented downward in the Fischer projection ring. And so we can go ahead and fill that in. Oriented downward at positions 2, 3, and 4 are going to be the groups that were on the right. So at position 2, there's a hydroxy group on the right there at position 2. So that's going to be oriented downward here. At position 3, we have a hydrogen atom oriented to the right, so that's what's going to be downward at that position. At position 4, we have a hydrogen oriented on the right, so that's going to be oriented downward. Right equals down when we go ahead and make the ring. And then at position 5, due to the fact that this is a D sugar, that means that this bit that tails along here, the CH2OH group, has to be oriented upward because it is referred to as a D sugar. And we know it's a D sugar because of the fact that in our structure here, the hydroxy group is oriented on the right of that penultimate carbon. Hydroxy group on the right of the penultimate carbon means it's a D sugar. So we fill that in, and then the last remaining piece here is our hydrogen atom. So just to confirm and double check that we've got the structure of alpha D-Galacto Pyranose drawn, we started with the structure of open chain D-Galacto, and it became referred to as Galacto Pyranose when it formed the 6-membered ring. Pyranose is a 6-atom ring, so we've got that in. The D portion we can recognize because the CH2OH group is oriented upward here. And we could also say in this open chain form is D because the hydroxy group of the next to the last carbon is oriented on the right. And then the alpha part of the name we have correct here because the alpha is referring to the configuration at the anomeric carbon. That carbon number 1 here, in other words, the hemiacetyl carbon is an ether group and a hydroxy group at that same position. It's alpha because the hydroxy group is oriented downward. So we can make those classifications here. So I'm going to go ahead and circle this now that we are hopefully confident in our answer to this problem. And hopefully you got the solution to that correctly as well. There are additional practice problems related to carbohydrates offered in the worksheet that goes along with this module. And I would definitely encourage you to give those problems a try sometime before you attempt the quiz later on down the road. So let's try the next example problem. And much like with the first example problem, if you haven't already tried to work this on your own by hitting pause, I would recommend you do that and then hit play to check your work. So we are looking at drawing the open chain form of beta D-glucosamine. And the structure that I have drawn for you below that is similar to a structure that you might see on the quiz is that of beta D-glucosamine. So the glucosamine structure, the amine part of that name, in case you're interested, comes from the fact that we have an amine group that has replaced one of the hydroxy groups that's in a typical carbohydrate, typical monosaccharide. So beta D-glucosamine, we've got the D configuration that we know because the CH2OH group is oriented upward here. Beta refers to the hydroxy group of that anomeric carbon as being oriented upward. And then now we're supposed to take this structure and work backwards to convert it into the open chain form. So let's go ahead and do that. And we will do that down here. So converting this into the open chain form, working backwards, the bond that we would be breaking here to do that is this bond between the carbon and the oxygen in the ring. That was the bond that we formed when we were doing the forward reaction. We were taking, for example, D-galactose, and we cyclized that by forming a bond between carbon number 1 and oxygen number 6 to make this link here. Now over here, that's the bond that we're breaking because we're working backwards. And what happens in that process of working backwards is that rather than going from, in the forward direction, an aldehyde to the hemiacetyl, instead we're going from the hemiacetyl at this anomeric carbon back to an aldehyde at that position. And so let's go ahead and do that. That's what's happening when we break that bond that I've shown with the squiggly red line. That's the weakest link within the structure. That's the one that's going to break to take us back in the other direction. So that's going to give us an aldehyde group within the molecule. That aldehyde group is going to be at position 1. And then we come around the ring to positions 2, 3, 4, 5. And we can go ahead and draw those out, represented by our Haworth projection. So I'm going to draw these 4 intersecting lines that represent those 4 carbons at positions 2, 3, 4, and 5. And we need to keep in mind the stereochemistry at each of these positions. So bear in mind that if the group is downward oriented in the ring, that means it is on the right in the open chain form. So the NH2 group, the amine group there at position 2, needs to be on the right in the open chain form. Hydrogen's going to be on the left. Coming on around the ring, the hydroxy group at position 3 is oriented upward. That means it's on the left. Hydrogen's on the right. At position 4, the hydroxy group is oriented downward. Down means to the right. At position 5, keeping in mind that this is a D sugar that was provided to us in the name, we can also decipher that from the structure here since the CH2OH group is pointed upward. That always means if it's a D sugar that the hydroxy group at this position, the next to the last carbon of the chain, is going to be on the right. Right indicates the D sugar. So put in the H there, and then finishing things off, we need that CH2OH group that we had in the original cyclic structure right here, highlighted in the cyclic structure with my laser pointer, is coming down to here to be the last piece of that puzzle. And so this is going to be our structure of the open chain form of beta D-glucosamine. And when we make the chain open, we don't really have to worry about whether this was an alpha or beta cyclic sugar, because once we open up the ring, we're going to lose that chirality at position 1. Position 1 is achiral in our open chain form because it's now an aldehyde group. An aldehyde group is trigonal planar. It doesn't have 4 different groups attached to it, and therefore it is not a chiral center any longer. So whether we started with alpha D-glucosamine or beta D-glucosamine, the product of opening up the ring is going to be the same. So with that, we will conclude this unit on converting between the cyclic form and the acyclic form. We will get back to some of this information later on in the semester as we apply it toward the field of chemical biology.